excuse me, how do these compare? And I want you to look at the differences between where I put the poles. These poles close to the unit circle as opposed to those which are farther from the unit circle. When the poles are closer to the unit circle, what happens?
Wouldn't it be steeper?
Yeah, right. You get a sharper response, so your response would be like that, and this one would be more like that.
Yeah.
Right? Now, I'm going to say, for example, R1 here is 0.95, and let's say R2 here is 0.6. That one's actually not going to be a very good bandpass filter, is it? Other one's going to be much sharper. But there's something else. Because the poles are there, the term in the denominator looks like z squared minus 2 times 0.95 cosine of something z plus 0.95 squared. And that one will look similar, except that it'll be 0.6 instead of 0.95. I'm just getting started. I haven't missed anything. And so, can you tell me what the transient terms in the impulse response will look like? The terms will look like h of n, r to the nth cosine whatever n u of n, right? Can you tell that? Complex conjugate poles. If you look at the the Z transforms we've derived, you'll be able to tell that, right? Do y'all agree with this? Now, I want you to look at something, and I may have mentioned it, and you may remember it from 431. I won't guarantee either of those, but I know I haven't mentioned it in here, and it's something I want you to consider there on the problem where it says the radii of the poles, in one case 0.5 and the other one 0.9 or 0.95. What is the difference? Now, I'll just call this omega. I don't know what it is. But what about that right there? If I were to ask you what this looks like, you would say, oh, it's gonna oscillate and decay, right? Do we all agree with that?
As long as R is less than 1.
Yeah, right. As long as R is less than 1. True. But what about those two cases? Is it going to decay a lot faster in one case than the other? Answer is yes. Which case? Plug these in. 0.6 to the n, 0.95 to the n. Which one's going to decay faster?
0.6?
0.6, right?
Yeah.
When you start 0.6, let's go to the 0th first second. It's going to go 1, 0.6, 0.36, 0.216, and I don't know the numbers after that. What about 0.95 to the n? It goes 1, 0.95, 0.9025, sounds right? Something like that. So this one, the impulse response decays. Yeah, it decays and oscillates, but it decays very quickly, like that. This one is going to decay and oscillate, but it's not going to decay very fast. Right? Now, knowing the following, that filtering means removing certain frequencies or something like that, right? Filtering really takes place once you reach steady state. What does that mean about these two filters? Which one of those is going to reach steady state sooner?
0.6.
That one, right? Okay, this one's a much better filter in terms of its gain response, but it's going to take longer to reach steady state. Is that a problem? Yeah, because until it reaches steady state, it's transient. The response is transient, and you're not really getting the filtering you want.
figured it would not be a problem because a lot of systems you can trash the first couple innings. Right?
Well, you are correct. And some, I might take issue with you saying a lot,
Okay.
but sometimes. However, and if that's true, then you're right. If you're sampling real fast and you can ignore the first few samples, yeah, because this one might take 20 or 30 or 50 samples for each steady state. But there's another issue, and I'm not arguing with you. I'm just saying this is another consideration. In some situations, and by the way, this is not a very good filter at all. It's horrendous. So it's not going to, even in steady state, it's not going to do a good job filtering. But in some situations, you might have a transient, let me back up, what's called a non-stationary. Ironic I'm mentioning that because that's where I'm going today. A non-stationary signal, meaning its characteristics change. Not just, of course the signal changes with time, but non-stationary means its statistical characteristics change with time. For example, you might have a signal and you might have some interference that you're trying to get rid of, and that interference may appear for a few milliseconds and then disappear. It appears and it's gone. It appears and it's gone. Okay, so intermittent interference. What's the problem with that? By the time this gets to where it's going to be removing it, the signal's already gone. Okay? You with me? So transient response, then the point I'm making, you are exactly right. In a lot of cases, no big deal. But the point I'm making is if you have noise or interference that appears and disappears just in short bursts, a good filter like this may not have time to reach steady state and filter it out before it's already gone anyway. So that's something else I want you to discuss. It says compare the two different situations. Probably problem number 3, 4, or something like that. Or if you're in 432, just skip that problem. Forget about it. Okay, but my point is, I want you to consider transient duration. And the frequency response, like a lot of things, there's a trade-off here. Your frequency response gets better as you push those poles toward the unit circle, but your transient response gets longer, and that's not a good thing. In some cases, it may not matter. In some cases, it will not matter. In some cases, if it's a problem, that is a problem. That's another consideration. Okay, that's what engineers get paid for, dealing with problems that don't have clear-cut answers, and knowing what the considerations are, and knowing how you balance the different considerations. Yes?
So I want to make sure I got that.
Okay.
So on the left,
Yeah.
it has a longer transient time,
Correct.
but it's a better filter.
It's right.
And so, and then on the right, it's got the opposite.
Right. It's not as good a, and by when we say better, we're meaning
Sharper, yeah.
sharper response. But that one's going to reach steady state much quicker. Oh, and by the way, I think I had you design also an FIR filter, which has only 2 or 3 terms in it. That means its transient response is whichever it is, 2 or 3 terms. Transients are gone. Okay? Because the impulse response is gone completely after that. So that's another thing, and you know that in terms of the gain response of filters, the FIR filter is not nearly as good as IR for comparable order. To get what I've got here and what I drew there, that's a second order filter, right? To get that kind of a response from an FIR filter, you may have to use a 40th or 50th order FIR filter. Okay? It's substantial. However, when that FIR filter, when that impulse response goes to 0, your transients are gone completely after that. Okay? Good with that? I was thinking about what direction I might go for the next few lectures earlier, and I decided I was thinking earlier today, what could I do to make the students as miserable as possible? And I thought, how about we combine random processes with signal processing? And that sounded like a really good idea to me. So let's do that. I want to talk for a week or two about what's called statistical signal processing. Very, very, very important area. And don't worry, everybody in here has had probability and some random processes. Yep. Communications? Not yet? Okay. Communications, yeah, at one point. Okay, don't worry. I'll keep you along with me here. So I am not going to go all the way back to probability, but I am going to go only no more than I have to. But I am going to go back to random variables. And so let me give you a few definitions. And I'm sure this is unexpected, so if you have questions, stop me and ask questions, please. Let's say that X and Y are random variables. And so, what does that mean? Okay, RVs. In here, RVs does not refer to recreational vehicles. Okay? Random variables. What is a random variable? It's a random variable, an RV, is a mapping of the outcomes of a random experiment, which I'm going to define shortly, onto the real numbers. And so, all right, let me define random experiment. A random experiment is an experiment whose outcome cannot be predicted exactly. And now, when I say exactly, what that implies is that doesn't mean that I can't say anything about it. I just can't predict what it is going to be exactly before I do the experiment. For example, and you might say, well, pretty much everything in the world is a random experiment, and to some extent, I think you can make that argument. Let's talk about some simple random experiments that we're familiar with and that are easy to describe. Just flip a coin, right? And look what turns up, heads or tails, right? Yeah, if you want to really experience this, I did this once upon a time. I'm lecturing to a 5-year-old son who's wanting somehow the subject, the idea of probability. I brought it up and I said, let me tell you about probability. And so we're sitting at the table here in the kitchen with a tile floor. Turns out to be important. We're sitting there, he's sitting on my knee, and I'm giving him this long lecture about probability, and I'm like, okay, pull out a quarter, and if I flip this, it's going to turn out to be heads or tails. And he says, yeah. And I said, can you tell me exactly what it's going to be? No. But we know it's going to be heads or tails, right? And he's, yeah. And so I said, okay. And what would you guess is the probability of it coming up heads or tails? And he said, probably 50-50. Okay, and I'm like, yeah, that's good. And so I flipped the coin to perform my random experiment. And no joke, that coin literally bounced a couple of times on the floor, rolled a little, stood up against the leg of the chair. And he's like, so Dad, how do we handle that? What was that? And I'm like, that's called a do-over. It couldn't have happened at any worse time, and he totally lost confidence in me. But we actually got a coin, didn't come up heads or tails, it stood on its side. Horrible lesson. I was just like, I'm humiliated. You just go on and play. Don't worry about probability. Hopefully it'll never be important in your life. But in a case like that, excluding that particular anomaly, a random experiment is just something we do, and we may be able to say something, in the case heads, tails, about the outcome, but we can't predict it exactly. Toss a die. You got 1, 2, 3, 4, 5, or 6 spots up. Okay? This is not not Game of Thrones. What's the other game where you use a 20-sided die?
D&D.
Yeah, Dungeons and Dragons. That's what I'm trying to think of. Or a 17. What are they? 20-sided and 17-sided or something?
There's a lot.
Oh, there's a lot. I wasn't aware of that. I've only seen a few. So, anyway, we can't predict the outcome exactly. Now, if you were to have a loaded die that is loaded in such a way, you all know what I mean by loaded, right? Unfair, somebody has tinkered with, has weighted one side of it. If it were loaded such that it comes up a 6 half the time, now, and somebody were to say, what can you say about it? What can you predict about the outcome? You say, I'm betting it comes up a 6. And half the time you would be right. 1 through 5, who knows? Let's just say they're all equal. So they'll come up 1/12 of the time. 1/12, 1/10. Okay, whichever. So, doesn't mean we don't know anything about the outcome, but we cannot predict it exactly. Now, a random variable is a random experiment where we map the outcomes onto real numbers. And some of them are fairly natural. If I were to, let's say, define a random variable this way, toss a fair die and define x, okay, I want to use capital X, capital Y when I need them for random variables, as the number of spots up. Okay? Then what does that mean? That means that X is either 1, 2, 3, 4, 5, or 6. Right? Only possibilities? Fair die, non-D&D die. And you say, oh, that makes sense. But I could define random variables a lot of different ways. The random variable is up to me to define. And so I could do it this way. Toss a fair die. And X equals, let's say 3.75 if the number of spots is even. Okay, so I've taken care of all the even. X is -1 if the number of spots equals, 1. X is -7 if the number of spots is 3. And X is pi if the number of spots is 5. Okay? Is that a random variable? Have I mapped the outcomes of a random experiment onto the real numbers? What are the outcomes? The number of spots. And when I did this, you said, oh yeah, I understand that. But what about down here? It's a mapping. I can do anything like that I want to. Now, there are some other cases, like if you toss an unfair coin. C-O-I-N. Toss an unfair coin that has a probability of heads of 0.6. Now, that means, and that's all I have to tell you about the experiment. But let's say that X is 1 if heads, and x is negative 1 if tails. Or, well, let's say x is 0. This is a particular kind of random variable. Do you all talk about this in communications?
Extensively.
I mean, oh, you do, really? In general, I was meaning about this particular one.
I mean, he touches on that, but we
Okay.
there's a lot of time spent on.
Oh, okay, good. So everybody will get to enjoy that. This particular random variable is called an indicator. Indicator random variable. And what does it indicate? If I flip it a bunch of times and I say 1, 0, 0, 0, 1, don't think binary. That counts how many, if you add the x's up, that counts how many heads you get. Right? That's what's known as an indicator random variable. And it indicates more than heads and tails, success and failure usually. So if something is a success, you say a 1. If it's a failure, you call it a 0. And the presence of a 1, in the long run, that'll count how many successes you have. Okay? But as far as I'm concerned, right here it's just a random variable. Okay? I took a random experiment whose outcomes are non-numerical, and I mapped them onto the real numbers. So that is just another example of a random variable. And I'll give you an even better example here. Let's say we select a resistor from a drawer labeled, let's say 1 kilo ohm, 5% resistors. So, what does that mean? Now we're going to assume that they are correctly labeled, so don't start talking about, well, what if we're in the 246 lab, because in there you never know what you'll get out of the 1 kilo ohm, 10% or 5% drawer. What does that mean? The only thing the manufacturer, when we order these resistors from Jameco, the only thing they're guaranteeing you is what? And measure its resistance. Now, that naturally has a numerical answer, doesn't it? I don't have to come up with some weird mapping. That'll be a number, and it will show up on my ohm meter. And the only thing the manufacturer guarantees is what? That it is within 5% of 1K. So we should say 950 less than or less than 1050. Okay? And that's all they're saying. That it's somewhere within 5, is that right? 5%? 1,000 would be 50, yeah. Okay, they're just guaranteeing you somewhere in between there. I got an interesting philosophical question. Should it be less than, or should it be less than or equal to, or doesn't matter, or don't care? Turns out it doesn't matter at all, right? Okay, and this is getting at the properties of that particular resistor. If I were to ask you, I'm jumping ahead and using the term probability, but I'm using it in an everyday sense. And what if I were to ask you, what is the probability that the resistance equals 1,000 ohms? What's the answer? You say 0. You've had a probability class before, haven't you? Even if you haven't, yeah, in math. Okay. Yeah, it's 0. Why? Good way to interpret it is, when I say what's the probability that it equals 1,000 ohms, I might be asking this: out to an infinite number of decimal places, ohms. And one way to answer that is, if you say, no, there's finite probability it's going to equal 1,000, then I would say, you just ain't measuring it accurately enough. Okay? And the problem here is that that is a real number. And the answer is, of course, 0. No matter how many decimal places, you just haven't measured it accurately enough. There are none in there that are exactly 1,000 ohms, because that means 1,000 ohms to infinite decimal places. So, but it's somewhere in there. I could ask something like this. What is the probability that, let's say, 999.1 is less than or equal to R is less than or equal to 1,000.1? And that probability is not 0. It's pretty small, but it's not 0, right? Because it's in a finite range. And so, equal to a particular value, the answer is going to be 0 here. We'll talk about how to calculate that later, and it's not that difficult. But by the way, that's exactly why this doesn't matter whether you put less than or equal to on those. The only difference between 950 less than R less than 1050 and 950 less than or equal to R less than or equal to 1050 is what? The exact values 950 and 1050. And the probability of those two are 0 anyway. Right. So, okay, we're getting a little bit of feeling for this, I hope. But let's see what else. Okay, so that's 0. So all they're guaranteeing, you're somewhere between 950 and 1,050. Well, what if you had a a probabilistic model for this is the following. For this, I'll say might be, because I don't want to be too definitive. Might be this. I'm going to draw a probability density function. Everybody heard of that? Sometimes, FUNCTION, abbreviated PDF, not to be confused with certain files that we all use. Probability density function. Has everybody heard of a probability density function? Okay? And this is what's called a uniform. So we denoted lowercase f sub r sub capital R with the variable being little r, and it's drawn like this, 950 up to 1,050, and that is not a probability. You all remember what that is? That's the derivative of the what function? Distribution, right? Distribution function. Has everybody heard of densities and distributions? Okay, good. Now, it turns out that the height of that rectangle is 0.01. Why? Don't know what property it has to have? It has to have an area of 1. Okay, its area is 1, and the reason is the area is the probability. And so, if you take the probability that the resistance is somewhere between 950 and 1,050, that's that entire area. And since that's the only place it can be, it has to have an area of 1, and therefore the amplitude is 0.01. And in the interest of confusing you thoroughly, even more thoroughly, I want to draw a distinction here. This is really fun, especially with seniors and graduate students. If I were to say, what is the probability that R is 1,000? You all know that that is 0, right? Okay. And by the way to find it here would be the probability that r is 1,000 would be the integral from 1,000 to 1,000 of 0.01 dr. Can you do that integral? Yes, you can. And what's the answer? You're integrating a finite function over a vanishingly small interval. And what is that? 0. Okay, the answer is 0. Would you also agree that the probability that r is 500 is also 0? You would agree with that? Yeah. Those are two very different answers, though. And you look at the right-hand side and you say, both of them are 0. Yes, they are. The reason this one's 0 is because this is called the impossible event. Okay? Impossible event. It cannot happen. What about r is 1,000? That's not an impossible event. Okay? Could r equals 1,000 happen? Yes, it just happens with 0 probability. Okay? 0 probability does not mean an impossible event. This means an impossible event. Why? Because that density function 500 is over here, and that density function is 0. That can never happen. 1,000 is right there. It just happens with 0 probability. It could happen. Okay, it absolutely could happen. It's just going to happen with 0 probability. This one can never happen, ever, and so that's called the impossible event. So the idea, an impossible event is not an event that has 0 probability, necessarily. It has to have 0 probability, but that's not sufficient. How does this compare to what you've seen in math classes?
I've seen it before.
Okay. Other than, you've seen all what I'm covering,
Just about.
but probably in about 3 months of class, right? With proofs all in between.
Yeah.
Okay.
You did this in data compression, didn't you?
I did.
Yes.
I think so. Oh, that's right. You were in there too. You were in there too. You were in there too. No, you weren't? Okay. All right. So, but I'm skipping a lot of the basic probability stuff up front. Okay. So we've got an impossible event. We've got a 0 probability event that is not the impossible event. It could happen. It just happens with 0 probability. So I'm going to define a couple more things, and one is the cumulative distribution function, and commonly abbreviated the CDF, and commonly just called the distribution, whereas this one is commonly just called the density. The CDF is defined, and we use capital F sub, in this case I'll use capital R of R. Now, the subscript is your random variable that you're talking about, and little r are the values it takes on. And the definition of the CDF is probability that capital R is less than or equal to little r. So, it's the probability that the random variable takes on values to the left of or equal to little r as a function of r. If we do that over there, if we take that resistor example, this is little r. I want you to look as I point here. What's the probability that the resistor is over there somewhere? 0, right? What's the probability that it's in there? 0, 0. And by in there, I mean from negative infinity up to that point. 0, 0, 0, 0, 0, 0. Okay, until I get to 950, the answer is obviously 0. Okay, but once I get beyond 950, what happens? At any point here, what's the probability, there's little r. What's the probability that it's less than or equal to that value? It's that area, correct? And that area as r increases, that area, keep in mind I'm talking about from negative infinity all the way up to r, that area is increasing how?
Linear.
Exponentially, linearly, quadratic?
Linear.
Linear? Right, it's linear, okay? Because the height of that little rectangle is fixed. As you move the width, it's increasing linearly with that movement. So it's ramping up. What about when you get to 1050? What do you say?
Yeah.
What is the probability that it's somewhere to the left of there? 1? Okay. What is the probability that it's somewhere to the left of there?
1.
1? Okay. What's the probability it's to the left of there? 1. Stays there. Okay. So, and I'm going to ask you to draw conclusions about this in general now. That is, goes up to 1. Starts off here. Okay, so there is our distribution function. Now, here is an unfortunate bit of terminology. That this is sometimes called a uniform distribution. Okay? I'll let slip what it should be called. It should be called a uniform density. But people will call this a uniform distribution. That's a distribution. Okay? This is a uniform density. By uniform, we mean flat over its maximum to minimum ranges. And so, uniform refers to the density function, but people call that a uniform distribution. There's all kinds of really bad terminology in the field of probability and random processes. And that's one example. So, we wind up with a distribution function that looks like this. Well, wait a minute, how are we going to get that? Tell me if this would describe what we just did mathematically. Capital F sub r of r, integral negative infinity up to r, of little f sub r of r dr. What was I asking you to do? I was asking you, what's the probability over there? And you were telling me 0. How are you getting 0? And I'll give you a hint. The answer was not, oh, just because it's 0 there. Because it's 0 everywhere over there. And when you integrate it, you get 0. Okay, how did I get the probability that you're to the left of a particular point here? I said area. Area is integral. Okay, so there is the relationship between the density function and distribution function. Y'all have seen an integral like that before, many times. It's called a running integral, right? Why is it running? I'm sure there's some good jokes in there. Why is it called a running integral? Because the upper limit runs along with time. And I made a major mistake. This cannot be r. Let's call it alpha. We need a dummy variable. Okay, because the upper limit is r. You're engineers, you don't care anyway, do you? Mathematicians get very excited by that. Okay, so if that's the relationship to get us from a density function to the distribution function, how would we go the other way? F sub lowercase capital R of lowercase r would be what? I go back the other way. Derivative, yeah. And it just so happens, d by dr of capital F sub r of r. It just so happens, we've said many times, oh, the derivative and the integral are inverse operations of one another. You got to be careful with that statement, because if that upper limit here is a constant, that is not true. If you integrate a function over constant limits, you've integrated the variable away, and the derivative of that would be 0. You're differentiating a constant. But something called Leibniz rule that you may have heard in calculus somewhere along the way, the derivative of this particular integral, with the upper limit being your variable, that is actually this relationship below it. You want to say something about that? Oh, okay. I saw you looking kind of strange at it. Or maybe you're just thinking, for a minute there, he reverted to mathematical rigor. I'll try not to slip up anymore. So, the relationship between the two. And by the way, let's check that. If I were to ask you to differentiate this function here, what would you get? Let's do it. I'm going to locate 950. I'm going to locate 1050. And this one over here, constant, derivative 0. Everybody agree? Okay, derivative 0. Over here, what's the derivative? Constant, derivative is 0. Okay. I'm going to send you all back to Calc 1. All right, what about in between? In between 950 and 1050, the slope is constant, so we can just do rise over run. Rise is 1, run is 100, so that's constant, which means we'll have a little rectangular pulse, 0.01. Does that look like that? Okay, good. Looks like we're right here. Some other properties. The capital F sub x, yeah, I'm not going to switch now. I'm going to keep using R, of negative infinity. That would be, what is the probability that it's less, R is less than negative infinity? What's probability? By the definition of negative infinity, what?
0.
There's nothing to the left, it's 0. That's what we mean by negative infinity. What about positive infinity? F sub R of infinity. Do we know what that is?
1.
1? Always? That means probability that R is less than or equal to infinity? Yeah. Okay, so that's 1. Do these agree here? We say starts off at 0, ends at 1. What about this? Obviously this can be flat, the distribution function. Obviously it can increase. Can it ever decrease? No, it can't. Why not? Because we could argue just from everyday experience, if I were to say it's to the, our random variables to the left of that, are we guaranteed that it is to the left of this? Yes? If we're in this range, we're definitely in that range. That's just a poor man's proof of this. F sub R of R is a monotonically non-decreasing function of R, little r. Okay, why did I not say monotonically increasing? What's the difference between the two? Monotonically increasing is always going up. Monotonically non-decreasing means that what? Could increase, but it could be flat also. Right. Okay, so, oh, and the other, I could add here, because the distribution function is a probability, it can never be negative, right? So, capital F sub R of R is always greater than or equal to 0. So it starts at 0, ends at 1, never decreases. And one last thing I want to add there is that the probability that A is less than, A is less than R, less than or equal to B, would be capital F sub R of B minus F sub R of A. And what that means is, assuming that B is greater than A. What that means is this, that if I wanted to know somewhere between A and B, right here, capital F of B would be the probability that R is less than or equal to B. Capital F of A is the probability that R is less than or equal to A. And the probability that A less than R less than or equal to B is F of B minus F of A, because F of B tells us what's the probability of being that over there. Capital F of A tells us the probability of being over there. And so the probability of being in between there is what? FB minus FA. Now, before we finish today, I'm going to give you corresponding properties for the density function, except they're not quite as many. What if, okay, properties of the density function. Okay, PDF. Well, let's see if we can get any of them from there. I like this one, and since I just talked about probability A less than R less than or equal to B, how do you get a probability from a density function? I'll give you a hint. This is a probability, isn't it? A distribution? Distribution is a probability. A density is not a probability. How do you get a distribution from a density? You integrate. Okay, so in this case, that will be the integral from A to B, f sub r of little r dr. Right? The integral gives you the probability of being in any particular interval, again, assuming B is greater than A. And if B is less than A, of course, the answer is 0. If B is less than A, what's the probability? The answer would be 0, because we're saying A is less than B. A is less than R and B is greater than R. Probability would be 0. Okay, so look at this property right here. Monotonically non-decreasing. What does that mean? Notice this is a derivative of it. If that is non-decreasing, what's its derivative? Always, it's either flat or it's going up. So its derivative is always
Positive. Positive.
positive, or and since it can be flat, it could be 0. So f sub r of r is greater than or equal to 0 for all r. And that's just simply a consequence of the distribution function being non-decreasing. If it were increasing, that would be greater than 0. But it can be flat, which means it also could be 0, so it's greater than or equal to 0. And that's about it on that, all right? So, let me tell you where we're going next time. We're going to talk about moments, correlation, etc. Okay?